Sample problem B. Identify the precipitate that forms when aqueous solutions of zinc nitrate and ammonium sulfide are combined. Write the equation for the possible double displacement reactions. Then write the formula equation, overall equation, and net ionic equation for the reaction. So the first thing that we need to do is identify the precipitates that will form. So the equation for the reaction is as follows. We had zinc nitrate dissolved in water, thus the AQ, and then ammonium sulfide also dissolved in water, another AQ, and the double displacement means that the positive ions will trade places or the negative ions will trade places, whichever you prefer in this, the couples trading places. So we'll have zinc sulfide and ammonium nitrate. We need to determine which one is going to be the precipitate and which one will just remain dissolved in water. So from table 1, it reveals that zinc sulfide is not a soluble sulfide and is therefore the precipitate. So we've identified that zinc sulfide will be the precipitate. So we'll, in the place of the parentheses, we're going to put an S for a solid. Ammonium nitrate from the table is also soluble, so that it will still remain in solution. So we can put an AQ after that. So the formula will look like this now. So where the first question mark was, we put an S because that's our precipitate, and an AQ for the second one because it will remain dissolved in water. So the overall ionic equation, the one where we show everything as ions, we have zinc nitrate, and notice that we have a 2 in front of nitrate because in the original formula there was a parentheses around the nitrate and a 2 subscript. And the same thing for the ammonium sulfide, we had a parentheses around the NH4 and a 2 subscript after that, so we have to put a 2 in front of it now because there's 2 ions. And then the products are zinc sulfide, which we have identified as being the precipitate, and an ammonium nitrate, which is still dissolved in water. So the net ionic equation is taking this original equation and looking for all the spectator ions, those ions that appear on both sides, which will be nitrate and ammonia. And what remains, and we'll cancel those out, and what remains is zinc sulfide, ZnS. So this is the actual reaction that's taking place. These two ions are more strongly attracted to each other than the water molecules' ability to pull them apart. The next idea is molecular compounds ionize in a polar solvent. So up to this point we've been talking about ionic compounds dissociating, and when they dissociate, they ions that were already combined are just separated from each other. Here we have a molecule that has no ions, but the polar solvent will pull it apart and form ions. So some molecular compounds can also form ions in solution, and usually these compounds are polar. And when this happens, the ions formed from a solute molecule by the action of the solvent is called ionization. So we're using a different word if we start out with a molecule and then form ions than we did for an ionic compound that just separated to form ions. This is ionization. Note that ionization is different from dissociation. When an ionic compound dissolves, the ions that already were present separate from one another, and when this molecular compound dissolves and ionizes in a polar solvent, these ions are formed when there were no ions present to begin with. Now, like all ions in aqueous solutions, the ions formed by such a molecular solute are hydrated. So each ion actually has water molecules attached to it, so that makes it hydrated. And in the process of forming that, when we learned that when ions or particles are attracted toward each other, they release energy. And so the energy that's released when ions are hydrated is actually going to heat up the solution. So if I were to dissolve something like hydrogen chloride gas in water, the water would become hot because of this process taking place. So in general, the extent to which a solute ionizes in a solution depends on the strength of the bonds within the molecule of the solute, and then also the strength of the attraction between the solute and the solvent molecules. So those factors will determine how well it ionizes. If the strength of the bond with the solute molecules is weaker than the attractive forces of the solvent molecules, then the covalent bonds in that molecule of solute will break and the molecule will separate to form ions. So hydrogen chloride dissolved in water will break apart and we'll have two ions forming that were not present to begin with. We'll have a hydrogen ion and a chloride ion. Many molecular compounds contain hydrogen atom that's bonded by a polar covalent bond, and some of these compounds ionize in aqueous solutions to release hydrogen. These are often acids. And that hydrogen ion attracts other molecules or ions so strongly that it does not normally exist alone. So even though we wrote it as HCl separating to a hydrogen ion and a chloride ion, in reality, that you wouldn't find them in the solution. They normally don't exist alone. So what happens, the ionization of the hydrogen chloride in water is better described as a chemical reaction in which a proton is transferred directly from the HCl to a water molecule. So let's look at that think about that hydrogen ion. That hydrogen ion is hydrogen atom without its electrons. And if you remember that a hydrogen atom is composed just of a proton and an electron cloud, so if we remove the electron cloud, all that left is a proton. This is a naked proton, so that H plus is actually just a proton. And it is strongly attracted to a water molecule where it's going to be covalently bonded to the oxygen end, which is the negative end of the water molecule. And so we'll end up having three hydrogens around the oxygen, and so we write it as H3O plus, the hydronium ion. So looking at our previous example, instead of having H plus on the right side, we have H3O plus. So there's actually the hydrogen ion is actually becoming hydrated to form the hydronium ion. So that's how you spell hydronium. And we'll use that word instead of the hydrogen ion. Next idea is electrolytes. We've talked about electrolytes before and non-electrolytes. And an electrolyte's strength depends on how many dissolved ions it contains. And substances that yield ions and conduct an electric current in solution are called electrolytes. So if I stuck two wires in it, they would conduct electricity through the solution to the other wire. Substances that do not yield ions and do not conduct an electric current in solution are non-electrolytes. Like dissolving sugar in water does not cause the water to conduct current because sugar is a non-electrolyte. The hydrogen halides, such as hydrogen chloride, is composed of a hydrogen that's bonded to one of the elements from group 17. Remember, group 17 is known as the halogens. And so we have fluorine, chlorine, bromine, and iodine are examples of that. And hydrogen halides are all molecular compounds with a single polar covalent bond. So these look like they should be substances that could ionize when placed in water. So all of these are gases. So hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide are all gases. And when you dissolve them in water, they're very soluble, and they're all electrolytes. Hydrogen chloride, hydrogen bromide, and hydrogen iodide strongly conduct an electric current when you dissolve them in water. However, hydrogen fluoride is kind of an exception here. Only weakly conducts current at the same concentration. And remember that fluoride fluorine had a very high electronegativity, has a very strong attraction for additional electrons. And the strength to which substances conduct an electric current is related to their ability to form ions. And so this would mean hydrogen fluoride doesn't form ions well. An electrolyte strength depends on how many dissolved ions it contains. So a strong electrolyte is going to be any compound whose dilute aqueous solutions conduct electricity well. This is due to the presence of all or almost all of the dissolved compound in the form of ions. So in other words, starting out with a molecular compound that's dissolved in water, all those molecules will break apart, or almost all of them will break apart to form ions, and you won't find any of the original, or very few of the original molecules present in the solution. So the distinguishing feature of a strong electrolyte is that to whatever extent they dissolve in water, they yield only ions. Now a weak electrolyte, on the other hand, is going to be some molecular compounds that when you dissolve them in water, they contain only dissolved ions, but they also contain molecules that haven't ionized. So you're going to have fewer ions formed because fewer of the molecules have broken apart through the action of the solvent. So hydrogen fluoride, as we said, was a weak electrolyte. And yes, it will form hydronium ions and fluoride ions, but I will still have a lot of the HF left in solution. So the concentration of dissolved intact HF is greater than the concentration of the hydronium ion or the fluoride ion. So hydrogen fluoride is going to be an example of a weak electrolyte. A weak electrolyte is any compound whose dilute aqueous solutions conduct electricity poorly. So because there's very few ions present, molecules don't conduct, only ions do, and thus it's due to the presence of a small amount of undissolved compound in the form of ions. There's not many ions that have formed. Now another example of a weak electrolyte is acetic acid, and there's a formula for it, CH3COOH. The first part there, minus the H at the end, is the acetate ion that you have memorized from your sheet. We learned it as C2H3O2, but you can see where that comes from. So acetic acid is another weak electrolyte, and we know it as the main ingredient in vinegar. So only a small percentage of the acetic acid molecules ionize in an aqueous solution. So in other words, they'll stay mostly intact, but it will break apart somewhat into a hydrogen ion, which becomes hydrated immediately to a hydronium ion, and an acetate ion. So it would look like the bottom formula right here. So we'll have the hydronium ion and the acetate ion, but we'll have a lot more of the CH3COOH that hasn't broken apart. So strong and weak electrolytes differ in the degree of ionization or dissociation. So now we're going back to a broader view right here of all electrolytes, those substances that had formula units that broke apart into ions because they already existed in ions, or molecules that have become ionized. So concentrated and dilute solutions differ in the amount of solute dissolved in a given quantity of substance. Okay, so the words concentrated and dilute only refer to the amount that's dissolved in a quantity of solution. And hydrochloric acid, we said, was a strong electrolyte, and acetic acid is going to be considered a weak electrolyte, even if you make it a very concentrated, like 10 molar. It's very concentrated, but because very few of the ions break apart, molecules break apart to form ions, it's going to be considered a weak electrolyte.